A normal mode is a pattern of motion that occurs when a system is excited or disturbed from its equilibrium position. It is a fundamental concept in physics and is often used to describe the behavior of various physical systems, including mechanical, electrical, and optical systems. In this virtual simulation, we will define what a normal mode is, discuss the properties of frequency, amplitude, and phase associated with it, and explain why different normal modes have different frequencies and why higher numbered modes have higher frequencies. First, let us define what a normal mode is. In simple terms, it is the natural frequency at which a system oscillates when it is given a small disturbance. For example, when you pluck a guitar string, it begins to vibrate at its natural frequency, which is one of its normal modes. Similarly, when you flick a pendulum, it swings back and forth at its own natural frequency, which is another type of normal mode. In both cases, the system returns to its equilibrium position after a certain period of time, which is determined by its normal mode. Now, let us discuss the properties of frequency, amplitude, and phase associated with a normal mode. Frequency is defined as the number of complete oscillations or cycles that occur in a given amount of time. In the case of a normal mode, it is the natural frequency at which a system oscillates when it is disturbed from its equilibrium position. Amplitude, on the other hand, is the maximum displacement of a system from its equilibrium position. In other words, it is the maximum distance the system moves away from its original position during oscillation. Phase, on the other hand, is a measure of the relative position of a system at any given time during an oscillation. It is usually expressed in degrees or radians and describes how much of a cycle has been completed at a given time. One of the interesting things about normal modes is that their frequencies are different for different systems. This is because the frequency of a normal mode depends on the properties of the system, such as its mass, stiffness, and geometry. For example, a guitar string and a pendulum have different frequencies because they have different masses and lengths. The frequency of a normal mode also depends on the restoring force acting on the system. In the case of a pendulum, the restoring force is gravity, while in a guitar string, it is tension. This difference in frequencies allows us to distinguish between different normal modes and study the properties of a system. Moreover, the frequencies of normal modes are not constant for all modes. Higher numbered modes have higher frequencies. This is because higher numbered modes involve more complex patterns of motion, involving multiple nodes, which are points of no displacement, and antinodes, which are the points of maximum displacement. As the number of nodes and antinodes increases, the frequency of the mode also increases, making higher numbered modes vibrate at faster rates than lower numbered ones.